Data is the keystone of Industry 4.0. Companies that want to leverage Industry 4.0 must consider data flow both within and outside the organization. The establishment of a digital thread of information throughout every department in a company is paramount. In addition, it is imperative to ensure data fidelity in departments that introduce new data like engineering, procurement, and manufacturing. If just one crucial portion of data is missing, it breaks the digital thread and the flow of information stops. Creating a digital thread of information is commonly implemented for the internal data a company generates, but what about supplier and partner data? The digital thread must extend beyond your internal operations to encompass supplier and partner data as well. Engineering data is the perfect example of why high-fidelity information is vital for internal and supplier data. High-fidelity CAD data, the missing link. Industry 4.0 is not possible until the correct data is present within CAD models in a format that can be read into mini-systems and is usable downstream from engineering. Engineering initiatives like model-based enterprise are the first steps to ensuring this happens, but there is still a long way to go. Model-based enterprise. Model-based enterprise uses CAD data as the single source of truth. Engineers must add all information relevant to downstream processes to CAD models, such as manufacturing data, MBD, supply chain information, pricing, and even maintenance and end-of-life data. Implementing a model-based enterprise initiative is an essential aspect of realizing Industry 4.0. For example, suppose engineers aren't entering all relevant data into the correct business systems at the source. In that case, no network speeds, machine learning, or artificial intelligence can bridge the low-quality data gap. Here are some examples of critical internal data. Model-based definition, MBD. In the past, engineers had to create a 3D CAD model first, then originate a 2D drawing with the exact measurements and manufacturing requirements. The manufacturing team would then translate the 2D drawing to a 3D model read by a CAM program or other manufacturing software. Unfortunately, the 3D CAD model wasn't compatible with manufacturing software programs. Therefore, the extra steps of manually translating to and from 2D CAD was a requirement. Because of these inefficiencies, some companies have introduced model-based definitions to their 3D CAD drawings. The idea of model-based definition is to provide all the product manufacturing information, PMI, like part dimensions, special instructions for CAM software, and other manufacturing needs, directly within the CAD format that can be read into manufacturing software. Thus, model-based definition cuts human costs, decreases lead time for manufacturing parts, and eliminates costly human errors from the process. Internally designed MBD CAD models should include PMI, Product Manufacturing Information. PMI is the data needed for manufacturing machines to produce a part. PMI is information like geometric dimensions and tolerances, GD&T, material and finishes, manufacturing notes and annotations, and critical design intent. Manufacturing companies use PMI to program machines and give guidance and specifications for the final component. Design intent. Design intent is the why and how behind an engineer's purpose in creating a component. It allows engineers to change 3D models while still maintaining the initial objective of the part. Data that shows design intent are attributes like annotations, the feature tree, history, and software-specific parametric programming. Much design intent is lost when translating from a native CAD format to a neutral CAD format. This is why it is vital to create a strategy whereby engineers use native CAD formats or where CAD is translated properly by CAD translation software as much as possible. Neutral CAD formats like STEP were created for long-term archival and are still best suited for that purpose because they don't preserve vital design intent information. Design intent data enables humans and machines to understand the why and how behind the design of a 3D CAD model. It provides critical data for other engineers, manufacturing, procurement professionals, and powers AI and machine learning. Motion study and kinematic information. Many physical components and downstream assemblies have moving parts. To enable simulation, testing, and digital twin capabilities, 3D CAD models must contain the proper metadata. That is, the data contained within data. The parts must be mated and constrained, have the full range of motion and kinematic data. Using this data, humans and machines can simulate how a CAD model will function within an assembly. Testing and simulation data. After engineers run testing and simulation programs, tolerances, point of failure information, and end-of-life data must be embedded into the metadata of each CAD model. In addition, test results and simulation data are vital for Industry 4.0 predictive maintenance. This type of projected function data is utilized by automation software that collects data in real time from IoT devices and compares it to the tests. The automation software can then make new projections based on analyzing the predicted function and actual function of the machines and components. Pricing and availability. To increase the efficiency and automate purchasing, engineering and procurement departments require pricing and availability information within CAD models metadata. Systems like Gedina's Part Solutions parts management software work as a catalyst for engineers and procurement professionals to access vital product information. Engineers can make better decisions if they have pricing and availability on parts that already exist in their PLM, PDM, and ERP systems. In addition, this type of information empowers engineers to reuse CAD models and CAD data from previous projects. Procurement professionals can find and ultimately automate purchasing decisions based on the geometry of a part using 3D shape search software to find similar CAD models in their systems. Parametric information. All parametric information needs to be accessible in different stages of the product lifecycle. Now more than ever, it's vital for people and machines in manufacturing, procurement, and sales to have access to 3D models. Furthermore, these models must contain accuracy even after being exported from the original native CAD format to a neutral CAD format or through structured data export like QIF. Data capture and communication are the first steps in the digital thread for manufacturing, ultimately leading to automated repeat purchases and leveraging machine learning to get better pricing from suppliers.